We start our exploration with an equation linking together three natural numbers, a, b, and m. M equals 6ab plus minus a plus minus b. This, of course, is not just a single equation. We have, in fact, four equations packed into one. Well, not really four, since the second and third ones are strictly equivalent due to symmetry. So, three equations, but to keep things simple, at least visually, we will keep using the shortcut version with plus minuses. A natural question to ask here could be, how many solutions, that is, how many pairs AB do satisfy the equation for any given m? Sometimes there will be only one solution, like with m equals 4 or m equals 8. Some other times, there will be multiple solutions, a non-trivial example of which would be m equals 29. And sometimes there are just none. In other words, these numbers simply cannot be written as 6ab plus minus a plus minus b. By the way, these dots are only meant to say that there are more of these numbers. How many more, you ask? Well, that's precisely the central question of this investigation. Is the cardinality of this set finite or infinite? The truth is, nobody has been able to give a definitive answer to that question. This is what is called an open problem in mathematics. Okay, I hear you. If it's an open problem, then it's clearly a very hard one, and we're extremely unlikely to find the answer. However, that shouldn't prevent us from trying to learn more about the problem. And who knows, perhaps can we even make some interesting progress? Let's give it a try. To begin with, let me save you guys a lot of time and pain. It is probably impossible to find a repeating pattern in the set itself, so we'll ignore it for the moment. Instead, let's take a closer look at the original equation. If we factorize a, we obtain something that we can describe as a parametric linear expression with variable a and parameter b. Now, let's see what happens when we set b to various values. With 1, we get. Next, with 2, we get. And so on. Alright, while it's far from being the whole picture, I think that's good enough to get ourselves some first impressions. An empty column means that the corresponding number is an element of our special set, and of course, a non-empty column means that the corresponding number isn't. This is column 66, and I believe it's clear that we can only be confident about the final status of the columns up to this point. Beyond it, we would need to collect more data, in other words, scan for higher values of b. Nonetheless, this grid allows us to express our goal in a very clear and visual way. Would we always find new empty columns if we were to extend this grid to infinity? Or is there a point along the number line after which we would necessarily fail to do so? As it happens, there are a couple of properties buried in this picture that could help us get a little closer to an answer. I need, however, to pause here for a minute and be upfront about the next steps. Up until this point, everything that was claimed was either completely self-evident or just trivial to prove. This was fine, but now I'm going to make a few unsupported claims, even though such claims would certainly require proofs. In my defense, this video isn't a peer-reviewed publication, and it would also get way too long and even more boring than it already is. So, I want to apologize in advance for the few times I'll be asking you to do the math yourselves. With that out of the way, let's study this grid more carefully. I'd like to draw your attention to this row, which corresponds to what I will call modulus 25 from now on. Notice what happens when we compare it with the row for modulus 5. Interesting, isn't it? Putting this into words, it would seem that, from the perspective of segregating empty columns from non-empty ones, the modulus 25 row is in fact redundant, as it is already included in the modulus 5 row. How about 49 and 7? Same result. How about we escalate things? What will happen with 35? Is it going to collide with both 5 and 7? Sure enough. Just to make sure that wasn't a fluke, what about 55? Should collide with 5 and 11, right? Correct again. Alright, now's the time to put on our mathematician hard hat and prove stuff. This will be our lemma number 1, which states that if a natural number n is congruent to plus minus b modulo 6b plus minus 1, where 6b plus minus 1 is not a prime, then n is also congruent to plus minus k modulo 6k plus minus 1, where 6k plus minus 1 is any divisor of 6b plus minus 1. By the way, I know that I'm playing a little fast and loose with the language and notation, but I hope it all remains clear for everyone. Here, for instance, I'm of course not claiming that a number can be congruent to two different residue classes modulo some number. The plus-minus symbol in this context just means that the proposition holds in both cases. As promised, I won't present a proof of this lemma here, but it's an easy one and you shouldn't have much difficulty with it. Alright, we have learned that we can safely ignore non-prime moduli. What else can we learn from this picture? There's a very nice symmetry hidden in here. Do you see it? Kinda cool, right? But please don't tell me you saw it immediately. It took me months before I first noticed it. Anyway, it looks like we can shave a large amount of redundant information here, like this. And if we now focus on the remaining data, we see that it can be split into domains of increasing sizes. Moreover, these domains of consecutive integers can be completely described with a single formula, namely this one. Of course, everything we just said needs to be supported by a second lemma, which I will neither prove nor bother to express in proper mathematical formalism. Basically, for any element of capital I sub n, congruences modulo primes greater than 6n plus 1 are irrelevant. This is getting exciting. Why? Well, provided we accept that lemma 1 and 2 are correct, we can now be quantitative, at least in a statistical sense. Let me show you. We need two ingredients for the calculation. First, the size of the capital I sub n sets. This is completely trivial algebra, and we find 12n plus 4. The second ingredient is a density, which I claim has this form. I will illustrate this formula with a concrete example. Removing two residue classes from the integers modulo 5 is equivalent to retaining 3 of them, right? Same thing with integers modulo 7. Now, by a direct application of the Chinese remainder theorem, we know that we will get 3 times 5 equals 15 different integers modulo 35. Therefore, the density of such numbers over the whole set of natural numbers will be 15 over 35. And in the general case, we will get a product over primes of p minus 2 over p, which we rewrite as 1 minus 2 over p. Now we can calculate an expectation of how many elements of our special capital A set we should find within the I sub n sets on average. This is simply the product of these two ingredients, of course. And we also obtain asymptotics. The size of I sub n is obviously order n. For the density d sub n, we're in luck, as it is a well-known asymptotic, namely order 1 over log square of n. So we now know that as n grows large, our expectation grows like n over log square of n, which is fantastic as this growth is without bounds. Moreover, when we observe the empirical data, we obtain a very satisfying confirmation. This plot shows measurements up to n equal 1000. We do see growth, and at precisely the rate we were expecting. So, is this it? Have we done it? Not quite. As this plot itself suggests, there is some variation in the distributions. The remaining problem is that we have no guarantees that the situation won't change, perhaps drastically, further up the number line. Let's illustrate this concern. Modular arithmetic is sometimes called clock arithmetic, so let's visualize a clock with a 35 minutes hour. These blue dots represent the 15 elements of the integers modulo 35 we were talking about earlier. And this yellow arc marks the domain of what we've called capital I sub 1. Now, it is absolutely possible to find 15 elements which aren't in I sub 1. Granted, that would be a very skewed distribution and incredible bad luck. But even if we try to ignore that such accidents could happen more easily in I sub 2 and subsequent sets, we can't exclude this possibility just with a statistical argument. Therefore, we need to show that the distributions stay quote-unquote reasonable. Intuitively, it does feel like these CRT-generated sets should be fairly well distributed in general, at least under some reasonable conditions. As it turns out, a paper published in 2008 on the subject does support that particular idea. The paper is titled Poisson Statistics via the Chinese Remainder Theorem, authored by Granville and Kurlberg, and their Theorem 1 provides us with an invaluable tool. Just to be clear, and using a typical Poisson terminology, the authors look at this picture and model it as 35 events happening in the span of 15 units of time, and the spacings represent the number of events happening in each unit of time. This is perfect for us, since we're interested in learning about how large these spacings can get. Our third lemma is now very easy to state. The Granville-Kurlberg theorem is applicable to our setup. As usual, I won't prove that statement, but I'll save you a little time by showing you how our study matches their requirements. The authors require an infinite set, capital Q, of square-free integers. We can simply define ours like this. Their omega sets are the CRT-generated ones we've been discussing. For example, the set of 15 integers we talked about earlier would be omega sub q sub 1. They also define S sub q measures, which are average spacings between elements of the omega sub q sets. You will be able to verify that these tend to infinity as required. And our S sub p are very simple and satisfy being a vanishing power of p. Your only challenge will be the counting function big N sub k. The authors present the very simple example of applying the theorem to Hooley's result. The difference in our case is that there is a positive error term that you will need to constrain properly to meet the theorem's requirements. And once you've done all of that, the result simply follows. Okay, let's assume that we accept lemma 3 as proven. What now? Well, we can now ask, what is the probability that our I sub n sets do not contain any elements of the CRT-generated sets that we dubbed omega sub q sub n? We understand that this probability has to be smaller than the probability that a spacing in omega is bigger than the size of I sub n, which we can equivalently express as 1 minus the probability of the spacings being smaller than that. Since we know that this is a Poisson distribution in the limit, we also know how to calculate that probability. This Q has nothing to do with the set defined in the paper. We're using the regularized upper incomplete gamma function here. Plugging in the actual values and leaving aside the derivation, you will find that this term tends extremely rapidly to 1, which in turn means that the left-hand side probability tends to 0 as n grows large. Therefore, and provided we accept the three lemmas we discussed as proven, we have no choice but to conclude that, as n grows large, it is an almost certainty that we will always find new elements to add to our original special set capital A. In other words, the set A is almost certainly infinite. Can we do better than that? I would imagine that applying a sieve would eventually work. Unfortunately, modern sieve theory is beyond me, and I barely managed to identify the problem in those terms. The best I could glean was that it would be a so-called small sieve with dimension kappa equal 2, perhaps? Even if that's correct, I never managed to derive any non-trivial lower bound, so maybe I'll learn sieve theory properly someday. So make sure to subscribe so you don't miss my next video on the topic in 20 years or so, okay? Alright, I guess it's time for the end credit scene. Here's the thing. If you are already familiar with the starting equation, then you definitely already know what I'm going to talk about. If not, then perhaps you noticed some familiar forms while watching the video, like that Merton's like product over primes, or that n over log square of n estimate. Well, those are no coincidences. The earliest proof I could find for this theorem was published at the end of the 18th century in the volume 12 of the Journal of the Imperial Academy of Sciences in St. Petersburg. I'm paraphrasing, but essentially what it says is this. I'm not going to elaborate here, but there's plenty of material to find online, like on the site of the Online Encyclopedia of Integer Sequences, where the sequence we've been calling capital A in the video is registered as sequence number A2822. Links are in the description. And yes, on the condition that you've convinced yourselves that the three lemmas we've discussed are correct, you can confidently claim that the twin prime conjecture is almost certainly true.